Last week we learned about wave refraction, the bending or changing of direction of a wave whenever it changes speed. Make sure you understand this process as we will encounter it again several more times this semester. This example of wave refraction in the ocean involves sound waves, which are a compressional wave, the same as the primary seismic waves. Sound waves actually travel better through water than air, and can cross entire ocean basins covering thousands of kilometers. One reason sound waves travel so far is that they are bent or refracted into a single zone in the ocean where the waves travel the slowest. Known as the SOFAR layer, it normally occurs about 1,000 meters beneath the surface. Sound waves bend towards this location where they move the slowest, then travel around the globe in this layer. Some whales actually take advantage of this layer to communicate with one another over thousands of kilometers of open ocean. Next, we need to investigate the vertical structure of the ocean. For this, we will use vertical profiles, such as the one shown here. This graph shows how the temperature of the ocean changes as you go from the surface down to the bottom of the ocean. The water at the surface is warmest because it is absorbing sunlight. But the water at the bottom of the ocean does not receive any solar energy and therefore remains quite cold. The region or zone of the ocean in between, where we change temperature, is known as the thermocline. It separates the warm surface water from the colder, deep water in the ocean. This vertical profile shows how the salinity of the ocean changes as you go from the surface down to the bottom. We'll get into salinity more in a minute. Basically, it is the amount of salt and other chemicals dissolved into the ocean. Water with a high salinity has lots of salt dissolved into it. The water with a lower salinity has less salt. The surface waters of the ocean have a slightly lower salinity than the water at the bottom because rainwater and rivers dilute the ocean's surface with fresh water. Rain and rivers do not enter the bottom of the ocean, so this water is not diluted and has a slightly higher salinity. The region or zone in between where the salinity changes is called the halocline. It separates the lower salinity surface water from the saltier deep water in the ocean. We also want to make a vertical profile of the ocean's density. Temperature and salinity are the two main things that control the density of ocean water, so we'll use them to figure out the ocean's density. Ocean water behaves a little differently than pure water. Salt water in the ocean will get denser and denser the colder it gets, while still remaining liquid. When ocean water freezes at about minus 1.7 degrees Celsius, the sea ice is lighter than liquid salt water. So, the warm water at the surface of the ocean is less dense than the cold water at the bottom. Salinity also affects water's density because adding salt to water adds mass to the water. The salt crystals have mass, and it does not change just because the salt dissolves. The salt's mass is added to the water when it dissolves. Because the volume of water remains almost unchanged when the salt dissolves, and density is equal to mass divided by volume, the higher the salinity, the denser the water. So the low salinity water at the surface is less dense than the saltier water at the bottom of the ocean. Adding together the effects of temperature and salinity, we find that the densest water in the ocean is at the bottom, and the least dense water is at the surface. In between is the region or zone where the density changes, called the pycnocline. It separates the light surface water from the heavier deep water. It is important to remember that the thermocline and halocline are what cause the pycnocline to exist. And because the lightest water is at the top of the ocean and the heaviest water is at the bottom, the ocean has density stratification and is therefore vertically stable. That is, ocean water does not want to move up or down. It is already where it wants to be according to its density. We can now make a simple three-layer model of the ocean. The uppermost layer, from the surface down to about 150 meters, is called the mixed layer because it gets mixed by wind and waves and contains the warm, low salinity, least dense water of the ocean. The middle layer, from 150 meters down to 1,000 meters, is called the pycnocline. And it contains the thermocline and halocline, which make the pycnocline. And then the lowest layer is called the deep water mass, from 1,000 meters down to the ocean bottom at 5 kilometers deep on average. It holds the colder, saltier, denser water in the ocean and makes up about 80% of the ocean's volume. Now these depths are simply averages. Near a coastline or near the poles, the transitions between layers will be shallower because sunlight does not penetrate as deep into the ocean. In the tropical open ocean, the transition will be even deeper as sunlight penetration is at its greatest. Our next topic is ocean chemistry, the chemistry of all the other stuff in the ocean besides water. So we are interested here in the salts, gases, and other materials dissolved into ocean water. To understand how salt dissolves, first remember that the water molecule is polar. It has a separation of electric charge. The oxygen side of water is negatively charged, while the hydrogen side carries a positive charge. We'll use sodium chloride, NaCl, to figure out how salts dissolve. It's nothing more than ordinary table salt and is the most common salt on Earth. The sodium atom has 1 electron in its outer electron shell, while chlorine has 7. But chlorine wants to get 1 additional electron to fill its outer shell. Sodium will transfer its electron to chlorine in what is called an ionic bond. This is what holds the atoms together to make a molecule of salt. And make sure you understand the difference between these ionic bonds and the covalent bonds found inside of a water molecule. Now, the chlorine atom has a negative charge because it has gained an electron, while the sodium atom carries a positive charge because it has lost an electron. When crystals of salt are put into water, opposite charges attract. The positive hydrogen side of a water molecule will be attracted to the negative chlorine atom, while the negative oxygen side of a different water molecule is attracted to the positive sodium atom. This attraction is so strong it rips the sodium and chlorine atoms apart from one another, and this is what it means to dissolve. The positively charged sodium atom and negatively charged chlorine atom are now ions. Atoms are molecules that are dissolved in water and carry an electric charge. The total of all the ions dissolved into water is known as salinity. It is expressed in parts per thousand, and on average makes up about 35 parts per thousand of ocean water, the rest being H2O. Oceanographers measure salinity in a couple of ways. They can evaporate away the water, or measure its density, or by how much light refracts when it passes through it. But the best method to calculate salinity is by measuring how much electricity a sample of water conducts. Absolutely pure water with nothing dissolved into it will not conduct any electricity at all. It is the ions dissolved into water that allow it to carry an electric current. And the more ions present, the better the water will conduct electricity. Now, one note. The water from your faucet at home, and even bottled water, has plenty of ions in it, and it will conduct electricity. Now, the main instrument oceanographers use to make vertical profiles like the ones we've seen is called a CTD. It is run up and down through the water from surface to bottom and measures electrical conductivity, for salinity, temperature, and depth the whole time. And if you know the water's salinity and temperature, then you know its density as well. Now, back when I was a graduate student researcher, I used a CTD aboard a ship called Flip. An incredibly strange, yet very stable, experimental research platform. I've included links to a video and website about it if you are more interested. And this is the same ship pictured on the cover of your laboratory manual. And we were out here using CTDs to make vertical profiles while investigating internal wave breaking in the ocean. So how do ions get into the ocean? Well, most come from rivers in exactly the same process that puts terrigenous sediment into the ocean. When rocks and minerals from land are broken into pieces by erosion, some of the rocks and minerals dissolve and are carried into the ocean by rivers. Ions not put into the ocean by rivers are called excess volatiles. And the main processes adding these ions to the ocean are hydrothermal vents. Remember, the color of this fluid comes from the huge amount of minerals dissolved into it. And also the fallout of ash and dust from volcanic eruptions. Now, because the ocean is in a steady state, its overall salinity is not changing. The amount of ions added to the ocean must exactly equal the amount of ions removed from the ocean. And ions can get removed when ocean water becomes trapped in sediments, gets subducted, or when organisms use dissolved ions to make shells. And more on this in a minute. Now, to figure out how long on average an ion stays in the ocean, we calculate their residence time. Take the total amount of that ion in the ocean and divide by its rate of addition into the ocean, or rate of removal, since input is equal to output. This tells us how much time passes between when an ion is added to the ocean and when it is removed. Now, we can also calculate the residence time of water in the ocean using the same formula. And it turns out to be right around 2,000 years. And this is going to be used as a dividing line to separate ions in the ocean into two groups. Ions with a residence time longer than water's, so longer than 2,000 years, are called conservative ions. They are evenly distributed throughout the ocean and tend not to participate in chemical reactions. Ions with residence time shorter than water's are called non-conservative ions. They are more active chemically, but are not evenly distributed across the world's oceans. Now, besides salts, gases can also dissolve into water. Oxygen is one example. Fish remove it from water with their gills. And the other extremely important dissolved gas is carbon dioxide. It dissolves into water by the three-step process shown above. And it turns out there is a lot more carbon dioxide dissolved into the ocean than there is as a gas in the atmosphere. Now, marine organisms use the carbonate ion from dissolved carbon dioxide, along with calcium ions from dissolved rocks, to make shells for themselves by recombining the ions into solid material called calcium carbonate. And this solid form is where the majority of carbon dioxide on Earth is found today. There's even more than is dissolved into water, and way more than is found in the atmosphere. Now, as one of the most important ions in the ocean and gases in the atmosphere, we need to understand how carbon dioxide cycles through the ocean. And there's going to be two basic pathways. One, the fast or biological carbon cycle, where plants in the ocean use dissolved carbon dioxide in photosynthesis, get eaten by animals, and the carbon dioxide through respiration is quickly returned to the ocean or atmosphere. Or, secondly, marine organisms use the dissolved carbon dioxide to make shells, which traps the gas in solid form for potentially millions of years in the slow or geological carbon cycle. Now, fossil fuels are produced as part of the slow cycle, and this is why we are going to run out of them soon. It takes the Earth a very long time to make fossil fuels. Biofuels, on the other hand, are made by the fast carbon cycle and represent an attractive alternative energy source since the Earth can replenish them quickly.